that I will explain along the way. So let me remind you very, very quickly what is the Gelfand-Kirillov dimension of an associative algebra. So if A is finitely generated, then and you take a finite dimensional generating subspace, then you look at the ascending filtration defined by the multiples of elements in V, and the Gelfand-Kirillov dimension is this number, this limit, which is written there, and it does not depend on the choice of V, and it plays the role of the Krull dimension of a commutative algebra. So if you have a commutative algebra, then the Gelfand-Kirillov dimension is just the Krull dimension. So this is one possible generalization to the non-commutative world of the Krull dimension, or the dimension of the associated variety. And this is according to experts, this is the best possible extension. And the problem where our results can be, the context of the problems, the context of the results we are going to tell you is the classification of Hopf algebras with finite Gelfand-Kirillov dimension, which is of course a very difficult problem. In particular, it contains the classification of finite dimensional Hopf algebras, those with Gelfand-Kirillov dimension 0, and it's which is still very open problem in general. So now I would like to remind you the notion of Nichols algebra, which is a very complicated notion and has several different definitions. So I will give you one definition, and maybe later in the talk by Schneider or by somebody else there will be other definitions. And to make things easier, I will just work in the context of abelian groups. So first of all, there is a definition of braided vector space. So the braided vector space is a vector space together with a linear isomorphism of V tensor V onto itself that satisfies this equation. This equation is called the braid equation, and it's equivalent to the Quantum-Yang-Baxter equation. And a way to find solutions to the braid equation, essentially due to Drinfeld, is to look at the category of Dieter-Drinfeld modules over any Hopf algebra. In this context, I will only consider Dieter-Drinfeld modules over the group algebra of an abelian group. And in that case, the definition of Dieter-Drinfeld module is a gamma-graded vector space, which at the same time has a left action in such a way that the grading is a grading of gamma modules. In other words, each homogeneous component is preserved by the action of gamma. And in this case, every braided vector space, every Dieter-Drinfeld module has a braiding, so a solution of the braid equation given by this formula. To braid V tensor W, you transpose them, and assuming that V is homogeneous, you let act the degree of homogeneity of V on W. And if V is not homogeneous, you extend by linearity. Okay? And what is the Nichols algebra of a Dieter-Drinfeld module? This is general, does not depend on the group algebra of a abelian group. This is for any Hopf algebra. So the Nichols algebra is a very interesting combinatorial object, which is a graded algebra, which is connected. It's a Hopf algebra in the category, which means if there is a comultiplication which preserves the multiplication but at the braided level, and is generated in degree 1, and at the same time the primitive elements are concentrated in degree 1. So there's a duality between the algebra and the coalgebra structure. And with this definition, there are several other ones. I would say 4 or 5 different other definitions, but I will stick to this one. Now, we have, so to speak, a forgetful functor from the Dieter-Drinfeld module category to the category of braided vector spaces, and the Nichols algebra does only depend on the braided vector space VC. This is technically important because one can realize the same Nichols algebra perhaps over very different Hopf algebras, and this gives us a lot of flexibility for calculations. On the other hand, there is a remark, an old remark by Matthias Grania, which says the following. If you take two Jeter-Drinfeld modules, you take the direct sum, and I assume that the following happens, so I would like to keep this here. So I go from V1 tensor V2 to V2 tensor V1 by the braiding. Then I go back. Then this commutes. So if this happens, then the Nichols algebra of V turns out to be the tensor product in the braided sense of the algebras B of V1 and B of V2. Therefore, the problem is when this does not happen, when C squared restricted to V1, V2, tensor V2 is not the identity. Okay. So what is the problem I would like to address, which fits into this context that I mentioned before? The problem is classifying Nichols algebra, say over abelian groups, with finite Gelfand-Kirillov dimension. And if I at least this contributes to the previous problem, because if you have any Hopf algebra, then you can take the semi-direct product called the bosonization, and then this semi-direct product, this bosonization, will be a usual Hopf algebra. And if gamma is a finitely generated abelian group and the dimension of V is finite, and if the Gelfand-Kirillov dimension of B of V is finite, then the Gelfand-Kirillov dimension of this bosonization will also be finite. So at least you find many new examples of such Hopf algebras. Okay, so let's start now with blocks. First of all, I say something which is already well known. Is what are the simple objects in this category? The simple objects are one-dimensional and are indexed by pairs Gk, where G is the degree of homogeneity of the one-dimensional vector space, and K gives the action. And the evaluation of K on G will be a label Q, and this label is the label of this simple object. And we know that this Nichols algebra is either a polynomial algebra in one variable whenever Q is 1 or is not a root of unity, and if Q is a root of unity, is a primitive root of unity of order n, then the Nichols algebra is a truncated polynomial algebra at x to the n. So this is known, and for later use I will use this notation. Gn is the group of n roots of unities, G prime n is the subset of primitive roots, and G infinity is the set of all roots. Okay. Now, if I have a Jeter-Drinfeld module, then as I said, I have a grading in homogeneous component, and since each homogeneous component is by definition a gamma module, then this is the composition of Jeter-Drinfeld modules. In particular, if the dimension of V is finite, what I will assume from now on, each Vg will be in itself a direct sum of indecomposable Jeter-Drinfeld modules, according to the action of gamma. So the action of gamma will decide this decomposition. So let me start by the case where our group is the cyclic group, infinite cyclic group, generated by this element G. And let me define V of epsilon L as the homogeneous, as the Jeter-Drinfeld module which is concentrated in homogeneous degree G, with dimension L, and such that the action of the generator of the cyclic group is given by a Jordan block of size L and eigenvalue epsilon. So this explains V of epsilon L. So L is the dimension and epsilon is the eigenvalue of the block. And so if you want the explicit shape of the braiding, it's like this, as I have in the slide. It has a basis indexed. So for me, on a notation I did not explain, this is this. So the first result is that the Gelfand-Kirillov dimension of a block is finite if and only if L is 2 and epsilon is either 1 or minus 1. I will explain a bit later how to prove this. And what are these two? So we have only two blocks, V12 and V minus 12. V12, the Nichols algebra of this guy, is the Jordan plane, which appeared, as far as I remember, in a paper by Gurevich more than 30 years ago, as far as I know. And this is a domain. This is a quadratic algebra generated by just one homogeneous quadratic equation, which is x1, x2 minus x1, x2, x1 minus x1, x2 plus 1/2 x1 square. And this algebra is a domain and has a PBW basis given by x1 to the a, x2 to the b. And the Gelfand-Kirillov dimension of this is 2. If you go to the other one, V of minus 1, 2, then we can prove that the Nichols algebra of V of minus 1, 2 is not quadratic anymore. It has one quadratic relation, which is x1 square, and therefore is not a domain anymore. It has nilpotent elements. And the other relation is cubic. It's x2, x21 minus x21, x2 minus x1, x21, where x21 is this element, and the symmetrizer of x1 and x2. And this element, this cubic relation, has to be understood as a kind of quantum cell relation. The basis of this algebra also has, all the algebras I will present have a PBW basis, and the basis is given by this rule, x1 to the a, x21 to the b, x2c to the c. And from that, well, a between 0 and 1, of course, and b and c are arbitrary. And the Gelfand-Kirillov dimension of this guy is 2. And as far as I know, this was new, was not known before. So to explain the proof of this result, and also it's very important to understand first the case of diagonal type. And I have to say that we do not have a complete answer on this case, on diagonal type, but we have a conjecture, and many of the results that come later depend on that conjecture. So if you have a semi-simple object in this category, it will direct sum of simple objects, and this will be a braided vector space of diagonal type, which means that the braiding is given by this formula, which I would like to repeat here. But Qij is not required to the condition Qij, Qji equal to 1. There are some technical reasons. We know what happens when Qii is 1, and I will, okay, but so we will assume that Qii is never 1. For simplicity of the notation, I will write Qi tilde j as the symmetrization of the matrix, and it's known that in lemma I proved with Schneider many years ago that essentially everything depends only on the QIG tilde, so on the symmetrization. Well, so what we want to do in general is we want to look at V's which are of this shape. And I will explain later the ingredients. And I will attach to V's like this a kind of Dinkin diagram. And the first step to attach a Dinkin diagram is to look at the semisimple case. So if I take this has both dimension 1, then I attach to this so to each VI of dimension 1 I attach a point which has label QII, and the other also has label QJJ because it's the other point. And if QIJ tilde is different from 1, then I add a line between them, and I label this line by QIJ tilde. And if QIJ tilde is 1, then we are in this case, because QIJ tilde is C squared at this level. Therefore, this is the not interesting case. Now, our conjecture is that if the Gelfand-Kirillov dimension is finite, then V has a finite generalized root system, which means that V is it's exactly as in the Heckenberger's classification on diagonal type. What do we know about this conjecture? We know that the conjecture is true if the dimension of V is 2, by more or less repeating what Heckenberger did when proved his classification. And we also have another two cases. One case was proved many years ago by Rosso, and then we extended this with Angiono. If Q is generic, which means that every Qij is 1 or not a root of unity, then the Gelfand-Kirillov dimension is finite if and only if Q is of finite Cartan type. And in general, we conjecture, or this is part of the previous conjecture, that if Q is of Cartan type, so Cartan type means that Qi tilde j, let me write this here. This means that where Aij is a generalized Cartan matrix, as in the book of Katz, then our conjecture is that if Q is of Cartan type, then the Gelfand-Kirillov dimension of B of V is finite, implies that it is of finite type. Of course, this conjecture is a particular case of the first conjecture, and we can prove that if if this matrix that appears here is of affine type, then the Gelfand-Kirillov dimension is finite. And why can we prove this for affine case and not in general? Because in the affine case there are lots of real roots, and we can reach the real roots with the action of the braid group, but we do not know how to handle the roots which are imaginary. So this is what is the technical abstraction at the moment with this. Infinite, yeah, sorry. So again, if A is of affine type, then you discard it. Okay, so the next point is the class where I have one block and one point. So not, because there are graphs that are not of Cartan type, so we cannot reduce to those. No? Already this is not true for Cartan matrices, because there are some system of matrices called hyperbolic, strongly hyperbolic, I don't remember, there are several names, which are exactly. If it contains an affine graph, it's okay, and if you want to prove this conjecture, the second one, the classification of matrices that do not have, that are not of a affine or finite type and contain an affine matrix is known. It goes up to dimension 11. And since we proved dimension 2, the remaining ones are very few. So probably by hand this conjecture can be proved. Okay. So essentially the next case is when V, again V is V1 plus V2. Here. This is a block. So this will be V of epsilon 2 with epsilon squared equal to 1. And this is a point. This is the next case we want to deal with. And I skip this technical notation because I will say it again in the next slide. And the question is, for such V, classify or determine when the Gelfand-Kirillov dimension is finite. So let me write down explicitly the braiding in this basis. Yes, exactly. This is a mistake. Yeah. Ivan pointed this mistake to me, but I forgot to. Okay? So, because I do not want to be in the diagonal case. Okay, so if I take all this data and I want to translate this to the language of braided vector space, it turns out that the braided vector space we are looking at is defined by a matrix Qij, of rank 2, where I will call epsilon Q11 because it corresponds to the block. And there is an A, which is essentially the value of the derivation that defines this block on the group like of the second component. And the braiding is given by this formula. So the first 2 rows and 2 columns, the first minor is the block, and the rest is this 3 by 3 is the point, and the rest is how C square or how C behaves between V1 and V2. And in terms of this relation, C square is the identity between V1 and V2 if and only if Q21, this is another mistake, Q21, Q12, so Q12 tilde is 1 and A is 0. Therefore, we need to take care of these two Q12 tilde, these two numbers, and A. And we will call Q12 tilde the interaction between the block and the point. And we will say the interaction is weak if this is 1, mild if this is -1, and strong if it is neither 1 nor -1. And we can assume that epsilon squared is 1. And then I will introduce a normalized version of A, which I will call the ghost. So the ghost is either A if the epsilon is -1, which is the value of the block, and -2A if epsilon is 1. And I will say that the ghost is discrete if J is a natural number, not 0. So the first lemma is that if the interaction is strong, then the Gelfand-Kirillov dimension is infinite. And if the interaction is mild and epsilon is 1, then the Gelfand-Kirillov dimension is also infinite. And in terms of this, I would like to have a pictorial description, and the pictorial description will be like this. So this means, so here I will put Q22. So in this case, the first two rows mean that the interaction is weak. That means in these two cases, Q12 tilde is equal to 1, and here Q12 tilde is minus 1. And this is the block. So this means that V1 is V12, and here is V minus 12. Okay. I would like to give the defining relations of the Nichols algebra at the same time of the classification, and for that I need some notation, which is very technical. Just I want to show that we do have the relations, and which may be useful for further work. So the result is the following. Suppose one has a braided vector space, which is a block plus a point, such that the braiding is given by this formula here. Then, if assume first that the interaction is weak, and that the ghost is different from 0, because if the ghost is 0 and the interaction is weak, then we are reduced to the remark of Granier. If the Gelfand-Kirillov dimension is finite, then we have one of the following cases. The first case is when G is discrete, and Q22 is equal to 1. And this we call the Lestrygonian algebra, and we denoted L of 1G. The Gelfand-Kirillov dimension of this guy is G plus 3, and this is a domain. And essentially, in this theorem, this is the only domain that we have. And the relations, we have some quadratic relations, but then we have relations of higher degree. Then we have the Lestrygonian minus 1G. Again, G should be discrete. And here are the relations. This is not a domain, and the Gelfand-Kirillov dimension is 2. Then we have one example where the ghost should be 1, and Q22 should be omega. So this is the only possible case out of 1 of minus 1 for omega. And this has Gelfand-Kirillov dimension 2, and here is the presentation. So far for the first two rows. And then for the first row, then the second row, when the block is minus, we have a family which is Lestrygon minus 1G. Again, it's not a domain because we have nilpotent elements, because it contains the block V minus 1, 2. And the Gelfand-Kirillov dimension is G plus 3. Another one, which is similar, but instead of 1 in the place of Q22, you have minus 1, and then you have a similar presentation. And this is all. The second result for this case is that if you have a braiding, but the interaction is mild, well, the previous theorem we proved without assuming the conjecture. So from now on, I have to assume the conjecture. So suppose that the conjecture of diagonal type is true, then there is only one possibility, which we call the cyclop. And the diagram is like this. It has a block of minus 1. It has a minus 1 on the point, and the interaction is minus 1. So minus means that it's mild, and 1 means that the ghost is 1. The Gelfand-Kirillov dimension of this guy is 2. Okay. About the proof of this, two results. So for the block, we filter the block, and then we get the filtration on the Nichols algebra and go to the associated graded and use the result on the affine case. In this case, when we have B of V1 direct sum V2, then we split this as B of V1 K, where K is the coinvariance of the action of V1. And it turns out, by a result of Heckenberger and Schneider, that this K, which is a graded algebra, is again a Nichols algebra of the piece K1. And K1 is the adjoint action of V1 on V2. Therefore, what we have to do in all these cases is to understand this braided vector space, which is technically involved, but at some point you get it. And when the interaction is weak, we always get diagonal type. But the interaction is mild, it's more difficult, and it's not of diagonal type, and we have to do it by hand, so to speak. Okay, however, in dimension 3, not all vector spaces are like this over an abelian group, or not all braided vector spaces are of this shape. So suppose you have again a block and you have a derivation. The derivation could be 0 on G1, but could be non-zero on G2. So this is the same as before, and this will not be of diagonal type. And we call this a paid block and a point, because it's a block that you do not see somehow. And in this case, we can prove that the Gelfand-Kirillov dimension is finite if and only if epsilon is -1, so the block is V -1, 2, and either Q12 tilde is 1 and Q22 is -1, in which case the Gelfand-Kirillov dimension is 1, are the other case is where Q22 is -1 as well as Q12 tilde, and in this case the Gelfand-Kirillov dimension is 2. And this is the only case that we found where the Gelfand-Kirillov dimension is 1 so far. So now I consider one block and several points. And so my general picture will be T will be the number of blocks, and these are points. And with all the notation that is needed, we can prove that, assuming first that epsilon is 1. So the first case is where we have two cases. All these are points. And then we have the other case. All these are points also. And the theorem is that in the first case, so if here you have a one block, then the Gelfand-Kirillov dimension is finite if and only if, well, I have to look, I do not assume that this is connected, and I look at the connected components of this braided vector space of diagonal type, and for each connected component, either the ghost is 0 or it is in some table, and we can tell you exactly what is the Gelfand-Kirillov dimension. And the table is as follows. Block and the point disappeared before, block at another point. So the first three here are blocks and 1 point. Then we have 1 block and 2 points. This is the only infinite series, 1 block and many points, which is, this many points is of, this is of Cartan type AN at q equal to -1. And then there is another small rank example, and all these examples are finite. So there are no series. There is only one infinite series, which is in the 3rd row. So somehow this is a very short list. For epsilon is -1, the list is even shorter, because we could have something which is away, so the interaction is weak and j is 0, but otherwise we have either 1 point or 2 points. And the first point is with weak interaction, and the second and the third are with mild interaction. And if there is one component with mild interaction, then all the others are disconnected from the block. So essentially it is connected, the diagram. So this is very, very restricted case. So the next case is when you have 2 blocks. So now I go to the case where you have V1 and V2. And these two are both are blocks. And assuming it is not reduced to a previous case, what we can prove is that the Gelfand-Kirillov dimension is finite if and only if the blocks are disconnected, which means that C square is the identity. And in such case, of course, well, we are assuming that the blocks are either 1, 2 or -1, 2. Okay, so this took us a while to understand this result, and once we have this, it was clearer how to give the general picture. So the general picture is like this. We have, these are blocks. And these are points. And in general, I attach to this a Dinkin diagram which has blocks like this or like this and points. And I connect them according to what I already said. And I will assume that this is connected in the sense that I introduce a pre-equivalence relation saying that 2 points are related if Cij, Cgi square is not the identity, and I take the generated equivalence relation and I assume that V is connected with respect to this. And I attach a graph as we discussed it. So if you have a block, you put a plus or a minus according to epsilon h. If you have a point, you put just a point with the label qjj, and we will draw an h if and only if they are connected by this relation, by the pre-relation, and the connection will be labeled by the ghost or minus the ghost in any case as exact. So locally is what I already explained, and if for points, again, I relate them by this rule, which I okay. And the result is as follows. So for each such diagram, for each V as in this class, we have a diagram with this decoration, a graph with this decoration. And we want to know in terms of this diagram when the Gelfand-Kirillov dimension is finite, and the theorem is to have a finite Gelfand-Kirillov dimension, you need to have no edges between blocks. If you have a connected component and one block, then the only possible connections between so X is the set of connected components. This is the diagonal part of the diagram, and X is the set of connected components. And for each connected component and one block, you can only have the possible interactions that I described before. So, for instance, like this or like this. For each connected component, only one point of the component is connected to a block. If the connected component has more than one element, it is connected to a unique block. If the connected component has one point, and this one point is labeled by a third root of unity, then it is connected to only one block. And if a block is connected to a point, then essentially we're by an H which has mild interaction, so it is labeled by -1 and the ghost, then there is no other H connecting this block with a point. So this last condition says that the only possible blocks are these ones. If you have, if somewhere you have weak interaction, you have only these two examples. Sorry, mild interaction. Okay. And for instance, let me try to finish the last diagram. So the diagram will be something like this. You will have here blocks, and here you will have connected components, and you will connect the components to the blocks according to these rules. For instance, if you take you can have something like this. And the diagrams we have only plus blocks and only ones classify the possible Nichols algebras of finite Gelfand-Kirillov dimension in this class that are domains. In all the other cases, they are not domains. And, well, the proof of this theorem, the really difficult part of the proof was the proof of one block and several points, because we had to discard, assuming the conjecture, many connected diagrams, and this, at least at the moment, I do not know how to do it in a more general way. We have to go more or less inductively. And once we proved this result, so what we did was to use this idea of getting K1 and looking at K1 and then deciding that it contains something which is not of finite type. In many cases, we found something which is of a fine type inside the Dinkin diagram, and then we do not need to use the conjecture but one of the previous theorems. But in many cases we had to reduce to the conjectures. And this is one of the largest chapter of the paper. And this also was somehow crucial to us. Maybe by psychological reasons we did not believe that this result would have to be true. But once we proved this, the rest, with all the techniques already available, went very fast, more or less. And to finish the classification, because this does not deal with all braided vector spaces, as I show you, the case of one pale block and one point is one case which is not of this class, but we believe this is feasible, but needs still a lot of work, which for the moment we have no time to do. So I think this is all what I wanted to do about this question. So thank you very much. Yeah, the pale block is that you have so V1 is a two-dimensional vector space which is of diagonal type. And this is a one-dimensional. But when you, so this is a block as a Jeter-Drinfeld module. So as a Jeter-Drinfeld module, the action of G is given by, in some basis, by a triangular matrix like this. And let me put here 1 and 1. And this is homogeneous of degree J1. And this is of diagonal type because we assume that eta of G1 is 0. Otherwise, we are in the previous case. Now, this is one-dimensional, then it should be related to K1, to K2 and G2. So K2 is the action, and G2 is the coaction, so it's the homogeneous component. And what happens is that eta of G2 is different from 0. And since eta of G2 is different from 0, the braiding is not of diagonal type. And it fails to be of diagonal type exactly at this point. And it's like it is a block of Jeter-Drinfeld modules, but it's not a block of braided vector spaces, this one. So in itself, it is of diagonal type, but the action is not. And you see, this affects the braiding between the block and the point. And for a long time, we found this recently. We believed there was nothing like this, but we were just we did not thought enough about this. But I would like to make a comment also, which I forgot. This result about the pale block and the point also proves the following thing. Together with the rest, it proves that, together with the first theorem about the blocks, it proves the following. If you have V, a Jeter-Drinfeld module over a group algebra, where gamma is an abelian group, and if the dimension of B of V is finite, then V is of diagonal type. Because in any other case, you will have any a block or a pale block and a point, and you will have something which has positive Gelfand-Kirillov dimension. This result I had in mind since 15 years ago. I never was able to prove it, so now I am very happy with this.